Hello, everybody. And before you all go into the well-deserved coffee break, let me quickly give you a good overview about how to use neuromorphic technologies for decoding of cortical activity and how this work contributes to that approach. Okay, I'm also in a very good place because two of the previous talks already laid a good baseline. So a few things you will already hear for the second time today. So let's just head right in. Paralysis is a medical condition that affects millions of patients worldwide constantly. And specifically, it is the inability to move some part or all of your body. Let's look at an example. Here we have patient X. Patient X, he wants to move his right arm. That works perfectly fine. However, when he tries to do the same with the other arm, that fails. And there could be multiple reasons for that. Muscle movement could be impaired, nervous system could be damaged. And modern medicine has an interesting approach to solving this problem, which is brain-machine interfaces, or BMIs, or also you can also call it brain-computer interfaces. Specifically, how this would look like is the following. You have a surgical procedure. The surgeons, they open the skull, and then they attach an interface to the cortex. This specific kind of BMI is called intercortical brain-machine interface because it sits right on the cortex. And what you then do is you connect this interface with a lot of cabling. The cabling goes into a machine, and then that machine kind of works with the data that's being recorded by the cortex or from the cortex. And that in turn can be used then, of course, to control something external, some external device like a prosthesis or an exoskeleton. And in here, for example, patient X now he has a prosthetic, and that is being controlled by the BMI, and hence he is now able to use his left arm again, and that makes him very happy. Of course, this would be a big upgrade for any patient that's really suffering from this condition. However, there's a few problems that current IBMIs have, and two of them are, let's say, the major ones. First of all, the surgical procedure, opening the skull, a lot of the times this is a permanent opening, and this permanent opening increases the risk of infection in the first place. Secondly, attaching this interface to the skull or to the cortex and then having this bulky wiring heavily impairs head movement of the patient, which is also a big downgrade in quality of life. Of course, there is on paper at least, in theory, there's a very easy solution to this problem. Just use wireless IBMIs. Okay, you don't have the cabling anymore. You also can, after the surgical procedure, at least you can close the skull again, and risk of infection drops immediately. However, of course, they in turn have a few hard requirements that are, first of all, and this is not so obvious, at least not for me, they demand a minimal heat dissipation. I think NIH, they published a white paper before saying that some implants in biological systems, they are not allowed to raise or decrease the body heat by more than 1 degree of Celsius, which is not a lot. You might know that those electrical circuits, they can really go up in temperature a lot during runtime. So 1 degree of Celsius is not a lot. And second, they of course have a restricted battery lifetime. You cannot just open the skull every time again to change the battery. So this has to be able to run on a long time. This means that we are very limited in bandwidth, and having a limited bandwidth, we want very high quality compression and very high energy efficiency. Those two things might already ring a lot of bells in your guys' heads. I know I'm in the right community here for this kind of thing. So what could be a promising candidate for such neural decoders? Well, of course, some kind of neuromorphic network. So for example, an SNN would be a very good fit for this. Or just to be more general, event-based neural networks or just neuromorphic technologies could be a good solution for this problem. Now, recently, this talk has increased. More and more people are considering this. And last year, Jason already talked about this. There was a BioCast challenge on exactly this topic, BioCast challenge on neural decoding. This was a collaborative effort by City University of Hong Kong, Harvard University, and TU Delft. I can quickly go through this because he already introduced some of the parts. They provided a data set and invited a lot of teams to compete, of course. The data set is the primate region data set. It is very interesting. You have two monkeys. They are named Indy and Loco. And their cortices were being recorded while following this target on the 2D screen. Now, you have the brain recordings, and the goal now is to decode these cortical spike trains into the original arm movement. And the challenge then specified 6 recordings for testing, 3 for each of the two monkeys. Now you need a good way to evaluate are the participants' approaches, and for that they use Neurobench. I don't need to tell you about it. I was planning to, but I think Jason did a very good job on this. In the end, you just give it your model, you give it your data, and then Neurobench spits out all the metrics that are important for evaluation. And please go and look at the tutorial tomorrow. I think it's a great tool to work with. Yeah. Finally, still, I mean, there's many ways to evaluate. You have many different metrics that could be important. So the challenge specified 2 tracks. Track number 1 was pure R2 score optimization, and track number 2 was co-optimization of R2 memory and operations. And just to give a quick explaining for R2, some of you might not know R2. R2 is basically, you could say it very bluntly, it's an accuracy metric for regression tasks. But if you're interested in the details, we can also talk about it later. And of course, both ANNs and SNNs will compete. Because it is a fair challenge in the end. All right. So I want to give you a quick overview about other approaches that were submitted. First of all, you have the baseline of Neurobench. This was just there in order to show, okay, this is a solvable task. Here is what's possible. And the architecture were just simple feed-forward networks consisting of ReLUs for the ANNs and LIFs for the SNNs. And yeah, some of the, let's say, more sophisticated approaches submitted to the challenge. One of them was a so-called A-GRU by Wang et al. This is from Shichi Liu's group at INI. They have an encoder GRU decoder architecture. And very interestingly, during training only, they have an additional auxiliary branch that was reconstructing the firing rates, which they report heavily helped with having good accuracy. This is especially interesting because for this kind of network, they are very complex during training, but relatively simple during inference, because during inference, they don't have this auxiliary branch. And this is important because Neurobench in the end evaluates the architecture that you use for inference, not for training. Having this architecture, they have very excellent accuracies, hence securing first place in track number 1. And another approach that I want to show you is the one by Liu et al. From Zhejiang University and Zenke Lab. They proposed this RSNN. Again, Jason already talked about it. I would still want to give a quick shout out to them. They have let's say, a simple lift-based SNN with explicit recurrency. However, that worked really well. They pre-trained all networks on all recordings, which was a method that we also adopted because it worked so well. And finally, they have very good compression methods, including iterative pruning and activity regularization. This again, as I said, it worked really well, so they have a very outstanding compression and hence secured first place in track number 2. Now, our approach looks like the following. We have a hybrid neural network consisting of a convolution and a lift-based network. The convolution is just a temporal 1D convolution, and the convolutional output then gets fed into a lift-based network with explicit recurrency. And then finally, this lift-based network, it predicts a few key points along the sequence that is to be predicted. And then we just interpolate back to original sequence length. This approach secured us 3rd place in both tracks out of 10 teams. I think that's fairly reasonable. And yeah, now you have all the basic knowledge that is important to understand the rest of the talk. Basically, this work that I'm presenting now, it focuses on further improvement of this approach and more specifically on how we can make our models real-time capable. And what that means, I will explain in a second. Okay. One of the things that are very important if you want to make your model fast, so real-time capable, is the buffering of the input data. Here at the bottom, those 4 points, and now it's probably good to use the laser pointer. Nice. Okay, so those points here at the bottom, those are the key points that are to be predicted, right? And all those blue marked area here, this is buffering and input data that is necessary in order to compute this one single point at the bottom. However, you will see that neighboring points, they kind of overlap regarding the things that they need to be computed. So already having computed the previous point, the things that you really need for the next one is this. Or let's say this is what is new. In order to compute everything, you need a few of the things that already have been computed for the previous time steps. So everything that is really important for computation is this. And one of the first things that we did in order to achieve faster models during inference is reducing our buffering from the whole thing to this. And this really not only increases latency, it also increases memory. So memory footprint also gets better by this. The second thing, exactly, yeah, and sorry, and all the models that we use and trained use this buffer architecture for inference. This is again important because, as I said before, the inference architecture now is more simple than a training architecture, and this is really what matters in the end for evaluation with Neurobench. The second thing that we did is look at the architecture of the convolution in the first place, of course. So having different number of convolutional layers, this scales differently in latency with the kernel size. And here you see this dashed line at the bottom. This is what we say is the maximum that we allow our models to have of latency. So if you look, we looked in neuroscience literature, and what they report is that the average time that a signal being produced by your cortex needs in order to actually result in muscle movement is around 100 milliseconds. Farah, she just said that 200 milliseconds is her goal. We stuck to the 100 milliseconds. So yeah, this is what we try to stay below if we want to achieve this real-time capability. And we now, regarding this, or looking at this, we have 2 models now. One of them we call benchmark-net for maximum R2 accuracy. We don't consider any of this and just go for whatever architecture is best for maximum R2. And then we have a real-time net, RT-net, for real-time capability, which considers all of this. We also have methods for compression, of course, including spike regularization, so penalizing a large amount of spikes being emitted by the network, as well as weight regularization, the same for the absolute weight values. This goes especially well together with quantization. We use fixed point quantization for our networks. 1 integer 7 fractional bits for the weights, and 1 integer 4 fractional bits for the buffers. And then lastly, of course, it would make sense to use pruning. I have to say that we miserably failed using pruning. I don't quite know why. I have done pruning a lot of times in my life, and after already like 10-15% of global unstructured pruning, so really basic pruning methods, our accuracy heavily degraded, and we are not quite sure why that is. And this is on top of the list for future work, just finding more sophisticated pruning methods in order to make this work, because this is an easy thing that you can do in order to achieve low memory footprints. Taking this, we apply all this to our real-time net, and this then yields our third model, small real-time net, which is just a compressed version of RT-net. And this then competes with the track 2 models, the co-optimization models. Okay, I will give you also some results from the hyperparameter optimization. There's many hyperparameters that we actually optimized in order to squeeze out every last bit of accuracy from the models. 2 things I think are very interesting. First, increasing the temporal kernel size seems to have a very good, one of the best influences on really getting a large accuracy. However, you cannot really do that in an unlimited fashion. First of all, of course, a large kernel size means you have a high memory footprint, which is bad. And second, of course, having more number of parameters also means higher computational load. So this is a trade-off that you have to consider. And we will speak more about this throughout the rest of the talk. Yeah, you will see what that really inflicts here. And second, as you can see in the right graph here, increasing the sequence length of the training data also has a very good influence. We are not quite sure where that ends because we couldn't afford to have very long sequences. So just to explain that quickly, those recordings in the data set, they are about 6 minutes long. And you can break that down into several samples and then batch them and train on batches. What you could also do is just have a very long single sample and train on that. And it looks like the longer the sample, the better the accuracy. However, of course, everybody that has trained with backpropagation through time before knows that training time scales quadratically with sequence length. So you cannot really, at some point it has to stop. Otherwise, a single sample will take months to train. So yeah, we are limited by training time here, sadly. Okay, let's look at some of the results. First, the models targeting R2 optimization only. At the bottom, you see our models. First thing that you can see is that we improved our previous results by roughly 7%, which we're very happy about, and also increased the state-of-the-art accuracy by roughly 1%. Additionally, you can see that when comparing BMNet and RTNet, trying to stay real-time capable costs you already a few percentage just because you need to have a small temporal kernel size in order to stay real-time capable, stay below the 100 seconds of, milliseconds of latency. Already costs you like 3% in accuracy, which is not so nice. But yeah, that's the way it is with this architecture at least. For the co-optimization models, we again improved by, if you look at this third line right here, we improved by roughly 11% compared to the previous models, which is very nice. We improved the state-of-the-art accuracy by 1.5%. And however, when it comes to memory, we are still larger by a factor of 4. And this is definitely due to the large kernel sizes of our models. Again, compared to our previous work, we increased the kernel size by a lot. However, the footprint went down, and this, I think, is a good sign for our compression methods. So they seem to have had a big influence, which is really cool. And lastly, and this is the most important thing, this was the target all along, our models are now real-time capable, which is nice. There is, however, one discussion that we have to have, which is about the computational load. And all of the other models, all of the other approaches, they are either purely SNN or purely ANN. That means they either only care about accumulated operations or MAC operations. You can give a relative cost of MAC to ACK. Leo et al., authors of TinyRSNN, they also report this. For 45 nanometer CMOS, the relative cost is for floating point operation roughly 5, for integers more like 30. That doesn't really matter because for any of these factors, looking at our max and x, we are, at least when it comes to number of operations, highly inefficient compared to TinyRSNN. And the question whether you want to have this extra 1.5% in accuracy, but in turn have 12,000 extra MAC operations is really a difficult question to answer and depends on your target platform, depends on your personal preference. And I should definitely mention this just to be transparent here. However, of course, we have a hybrid network. I think this is a very interesting point. We have a hybrid network. The convolutional and spiking subnets, they are separable. And this would enable a deployment on a hybrid hardware platform, consisting, for example, of convolutional or CNN accelerators and neuromorphic accelerators. This is very interesting, I think, and this would truly enable a fair comparison at runtime. But yeah. Another point that I want to make quickly, the last few minutes, is that for the second monkey, Loco, not only did the data consist of motor cortex recordings, it also consisted of somatosensory cortex recordings. So the motor cortex, roughly there, is there for planning, controlling, execution of muscle movements. This is the obvious cortex when you think about neural decoding, motor neural recording, decoding. This sensomotory cortex, this processes tactile and sensory information. So if your neighbor just taps you on the shoulder, for example, this is the brain area that gets activated, and those two are highly coupled. And we have both types of data. So yeah, we thought what we could do with that. Looking at the results, and for now, I want you to focus on the blue and the red bars for now. You can see that having the blue is only M1 data, red is only S1 data. Decoding from motor cortex data works far better than decoding from somatosensory cortex data. However, if you now focus on the middle one, so the beige one, this is just stacking both types of data and feeding it through the network. Having both data actually on average works a little better. So M1 works better, but seems like S1 data can complement the M1 data. And then we tried those two approaches, pre-live, post-live, basically having separate convolutional blocks for M1 and S1 data and having both separate convolutional blocks and spiking blocks for both types of data. And having this kind of separate treatment for both data types didn't really do anything for us. However, we are convinced that there are some more sophisticated methods in order to have this nice baseline of M1 decoding and then aiding this with additional data from the S1 cortex. So yeah, we are not sure what this could be, but maybe other papers in the future will answer this question. Okay, to give a quick summary, neuromorphic computing is a very promising approach to solving all these problems that come with IBM eyes and wireless IBM eyes. And this data set, the primary region data set, which is offered by Neurobench, seems to be a very nice benchmark for efficient AI when it comes to sequence decoding tasks. Finally, our network was improved by a lot and also improved upon the state-of-the-art accuracy just by scaling up sequence length as well as the kernel size and of the temporal convolution. However, having this large kernel size makes it very hard to efficiently compress our models. And yeah, this has to be considered, of course. Finally, for the final step of this project, we want to deploy our networks on hybrid hardware platforms for evaluation at runtime. If some of you in the audience have some remarks there, maybe know a platform that would be useful for this or have just experience with this and want to yeah, give us some info, please get in touch with us. And yeah. That's been it. I want to quickly give a thanks to all my colleagues here, especially this handsome guy in the middle, Alex, which I worked with very closely when doing this project. And this is a picture that we took 2 days ago here at NICE. All of my colleagues are here, and we're having a great time. Thanks again to the organizers, and thanks to you for your attention. If you have any questions, let me know.